por asistir a este evento regional. Para iniciar, como hicimos
Thank you for attending this regional event. And I'm going to pass the microphone for the people responsible for interpretation to explain how to use it. Gracias por asistir a este evento regional. Doy pase a las personas que nos van a apoyar con la traducción. Brindan información a los participantes que se encuentran en la sala Zoom sobre la traducción en línea. Fiona, adelante.
La interpretación ya ha sido habilitada, así que si ustedes necesitan interpretación de inglés a español, verán que en la parte de abajo de su pantalla, donde tienen su barra de control, les aparece un botón que se llama interpretación con un icono de globo. Pueden hacer clic sobre ese botón y seleccionar la opción de español. Así que cada vez que alguien hable en inglés, ustedes escucharán que recibirán la interpretación de inglés a español. So the interpretation has been enabled. At the bottom of your screen on your control bar, you'll see a button called interpretation with a globe icon. Please click on that button if you need interpretation from Spanish into English, and then select the English option. That way, whenever somebody speaks in Spanish, you'll automatically get the interpretation into English, and that's all you have to do. Thank you. Muchas gracias.
Muchas gracias, Fiona, por la información.
Thank you, Fiona, for this information. So we'll just give you a few seconds so that you can select the language you wish to hear. Gracias por la información, Fiona. Ahora les doy unos segundos para que puedan seleccionar el idioma que desean escuchar. So let's give a warm welcome to the second and final day of this annual conference that's being held for the third consecutive year, called Metrology for Digital Transformation. My name is Germán Romero from the National Metrology Institute of Colombia, INM Colombia, and I will be with you today as the Master of Ceremonies. This event, we should remember, is also being transmitted on Facebook and YouTube from different institutes. So we'd like to welcome all of you who are connected on social networks. And I'd like to remind you that in the chat, you will be able to see the links so that you can share this event with your colleagues. This conference is organized by the Working Group 14, M4DT, of the Inter-American Metrology System, SIM, SIM. And before starting, as we did yesterday, we'd like to remind you of some important guidelines for this conference. In the first place, I'd like to tell you that this event is being recorded from beginning to end. The videos and slides will be available on the webpage where you registered for this event. Also, I'd like to ask you to turn off your microphones and cameras. Also important is that your questions you can enter in the chat during the different presentations. And once we conclude the presentation, then the block of presentations, the speakers can answer your questions. When you ask questions, please remember to indicate who the questions is for. Also, you can ask questions during the presentation in the chat, and you don't necessarily have to wait until the person finishes their presentation. So I'd like to give the floor to Fernando Kornblit to say some words to inaugurate this second day. Fernando Kornblit graduated in mathematics with applied statistics and a postgraduate degree in industrial quality. He's a member of the National Industrial Technology Institute, INTI, of Argentina, and since 2014, head of the quality department for measurements, and he has broad experience in evaluating uncertainty, statistical tools for laboratories, and also as a peer reviser for different national metrology institutes. Between 2012 and 2016, he was the chair of the working group of the SIM on mass and related quantities, and since 2004, the representative of INTI on a working group of the quality system of SIM, QSTF. This is why it is an honor, and we're grateful to have him with us and to say a few words of welcome during the second day of the conference. So please go ahead. Thank you very much. Welcome all. It is a pleasure for me to be able to greet you all and welcome you. It would seem that, well, a long time ago was when we held the first SIM conference on metrology for digital transformation, but it was in July 2020, in the middle of the pandemic, when we were starting to take our initial steps with the Zoom meetings or using virtual platforms. So in that period of time, 2 years ago, it's impressive how much we've learned, how much we've progressed regarding digital transformation. Yesterday, we were hearing about digital calibration certification, metrological support for the 4.0 industry. And now we're going to hear about two very important topics. We're going to speak about the automation of laboratories, and we're going to hear some speakers who will be speaking about the automation of laboratories and also industrial automation. This is a task that we've been involved in for many years. However, in recent years, in the context of the process of digitization that's more accelerated, the efforts for digitizing the measurement systems and also the management systems associated to these measurement systems. All of these efforts to achieve digitization have really been growing and have become more generalized, particularly the digitization linked to the generation of digital certificates. There will be a presentation on this today. And then we're going to speak about another topic that's also quite interesting, the relation between metrology and artificial intelligence. It's a two-way relationship, because the algorithms of artificial intelligence are very often based on measurements, and metrology has to make or guarantee the reliability of these measurements and to guarantee the good results. On the other hand, metrology can also take advantage of the algorithms for achieving better measurements. So this these challenges are very interesting ones, and we will be hearing about some of those today. Well, I don't want to take any more of your time, because the interesting thing today is what's coming up, these talks. So we'll see you at the end. Thank you and welcome all. Fernando, thank you very much for your words of welcome. And as you were saying, then we will officially begin the second day of the conference. The first block has 3 presentations about process automation, and at the end of the block, we, as always, will have a round of questions and answers, with our first moderator, Rubén Gil. Rubén is an engineer in telecommunications, graduated in a master's degree in electronic sciences, including automation and control. He has experience in project development and service development in the area of gas flows in Peru, such as calibrations, verifications. He's a technical expert as an auditor of metrological verification units. He has experience developing hardware and software for digitization, automation of measurement process, and participates actively in topics of digital transformation, such as Metrology for 4.0 industry and digital calibration certificates. He's a member representative of Peru before the Metrology Working Group 14, called Metrology for Digital Transformation, or the SIM, and he is the current coordinator of a sub-working group, Automation of Laboratory Processes, of the 14 working group of the SIM. Rubén, thank you for your support during this block of presentations. And let's go on with our first speaker, Aldo García, who will be talking about digitization for the generation of digital calibration certificates. Aldo has broad experience in project and service development for the area of vibrations and acoustics, or CENAM Mexico, knowledge applied to measuring vibrations and acoustics, experience in calibration services, develop and optimization of measurement systems through instrumentation and control of serials of different transductors, as well as knowledge of programming, standards for measurement laboratories, estimation of uncertainties, and the implementation of agile models. Aldo participates actively in digital transformation as the 4.0 industry, 4.0 metrology, digital calibration certificates, remote sensors, and metrological cloud. He actually leads one of the working groups on digital transformation under the name of Agile Projects. It's a privilege to have your participation in this event, Aldo, and I'd like to give you the microphone so that you can begin. Welcome. Thank you, Herman, and I'd like to thank all of the colleagues present today. And so we will go on. I will share my screen.
Thank you all for being here.
Gracias por estar acá para esta presentación.
Digitalization for the generation of the DCC. And I am your host in this presentation, Aldo García. I'm going to begin this presentation giving you a definition of this digitalization, and then I'm going to explain the different stages of the digital transformation, how we can go through these different stages to achieve the digital transformation. And I'm going to explain each one of these definitions. For example, I'm going to begin with digitization. Is the core of the third revolution. It is all about converting analog things into series of zeros and ones digits, making the fundamental element universal. Digitalization, in the other way, marks the way to the fourth revolution, which means the process the zeros and ones into meaningful value for convenient consumption. Digitalization improves specific processes, and digital transformation crosses all the borders between companies and systems, permitting the combination of all sorts of diverse digital and digitalization solutions. It helps build or select the best solution to specify needs and even conveniently and seamlessly combine them with each other of enhanced value, because the fundamental element is so universal that it covers digital content and context. This unification of things improves the processes and functionality that we might not have conceived before. So this is the thing that I want to share with you. We have these different steps in order to achieve the digital transformation. Right now, so many laboratories in metrology are in the digitalization steps, and they are looking to the digital transformation, sorry. So I have explained these different stages, and now I'm going to share with you our vision in a specific way through a laboratory in CENAM that we want to make these steps in order to achieve the digital transformation. So if you remember the definition of digital transformation that crosses the borders between companies and systems, I give it to you this definition that I have written for you. In a few words, for me, digital transformation in metrology is the usage of computers, instruments, IT technologies to automate and optimize a process through the exchange of standardized data between machines in order to give the traceability among the metrology value chain. And if you can see at the right side of this presentation, I have more or less how I am thinking this can be done. So we have national calibration references in the NMI, in different NMIs, and then we have transfer references. In this way, we generate digital calibration certificates. And here we have the traceability. But which is the way that we are going to achieve this crossing borders to our users? We are going to use meta languages like XML. In this way, using these meta languages, we can cross these barriers and give all the information between machines, not for human. This information is for machines in order to take advantage of the reduction of the error made by the human, and the process can be faster. So we can have data between different companies and take advantage of this information to have control and to have to the final value chain the most important aspect of the DCC, that we are going to have traceability. So we have users that can be Industry 4.0, government, smart cities. There is a lot of users that can use this DCC, and we have already noticed this. We are collaborating right now with different companies working together to achieve this vision, to share information in real time and improve the processes between different companies. So we need to digitalize the systems. And this will give us the opportunity to develop and use different tools like intelligent artificials and different tools like digital twins. And this will be a very useful in the future to have better communication of the data, to have traceability, to have metrological assurance of the magnitudes that we are measuring. And in this way, we are talking about digital transformation. So this is our vision of how we see digital transformation in metrology. Then I want to share this with you. We are defining the strategy. We need to be, we need to think in one way to have a standardized way to share the information. So that's why I'm sharing with you this. This is from the PTV colleagues and explains the different levels that we want to go through. For sure, we are going to add more levels because any NMI is different and they have to achieve the level number 5 in different ways. So maybe we need to improve between level 1 or 2 or level 2 or 3 different middlewares in order to achieve these different approaches. So I'm going to read it very fast. The level 0 is paper. We will share the digital calibration, the calibration of a document in paper, sorry. Then we go through the PDF. It's a digital document, but it's for human readable. The level 2 is machine readable document. Level 3, machine readable and executable content. Level 4, machine readable and interpretable content. And the final level 5 is machine controllable content. So we are aligned to this vision. For sure, and I'm telling you again, we are thinking that maybe we need to add more levels between these different steps. So in this presentation, I want to propose steps in order to implement the DCC in a laboratory. For sure, this is our vision, and maybe this can be different for different NMIs. But I want to share with you this because I want to know if there is another NMI that is interested or are reproducing these kind of steps. It will be very useful to all of us to share this kind of information, because in order to achieve the artificial intelligence using the metrology and traceability, we need to get in touch and share this kind of ideas. So number one is selection of a pilot laboratories for the implementation of the digital calibration certificate. We have an NMI, we are in an NMI, so we need to look at the best pilot project in order to implement the DCC, and this will give us the opportunity to understand our challenge that we need to afford in order to achieve the DCC. So the step number one, select the pilot laboratory for implementation of the digital calibration certificate. Then we know to know the metrological technology readiness level of the laboratory. We need to identify the kind of digitalization level. So in this part, we need to look at this laboratory and understand the process of the calibration, the calibration chain, the different instruments that are involved in the calibration chain, and then the level of technology that they can give us in terms of digitalization. If these instruments can provide us already digitalized information, or we need to implement the solutions like image recognition in order to read the analog indicators or digital indicators. We need to identify this kind of metrological technology readiness level in order to understand the instruments and then the process, because maybe we can use some software, or we are using Excel or data sheets, calculation data sheets, or software that is not free or open source. We need to identify these kind of things in our laboratory. Then identification of a pilot project of calibration services for the digitalization and later implementation of the digital calibration certificate. We need to understand the prioritization that is defined with the comparison of aspects such as complexity of the service against automation. So we need to understand this calibration chain. We need to understand if exists in the laboratory one service that is the easiest to implement, or then we need to understand if it's full automated or it's semi-automated calibration process in order to select the best option. Then we need to understand, maybe this is an extra thing that I think is interesting, the number of calibration per year. Maybe this indicator give us information if we put the effort developing the DCC with this service can be or can have an impact to the final users. Sorry. And then we have the number 4, identify DCC dependencies into the calibration process. So we are going to look into the different processes or steps in order to develop a calibration. And we are going to generate a pilot DCC sub-scheme from calibration references like primary references, instrumentation chain components, and uncertainty sources that are included in the process. Then we are going to select the best roadmap in order to achieve the established goals to get, this is the objectives, sorry, get experience, or maybe you are going to have you are going to solve a user request, or you are going to solve a requirement from the user needs. So we need to understand why we are going to implement the DCC in this first laboratory and then these services. And then the final step, for sure, I think we have a lot of more steps, is follow or propose good practices for the quantity of interest. So I'm going to go through a user case. So we are, for the number one, we are going to implement DCC at secondary calibration laboratory of alternating acceleration. The step number two, we implement the metrological technological readiness level. We have an intermediate level because we have metrologist intervention. So we are going to use Excel for the calculation of the data and LabVIEW to automate the measurements. The step number three, we have calibration of accelerometer calibrators. We identify this service because it's the easiest service of calibration regarding the measurement chain and calibration time. And it's one of the most used calibration services at the laboratory. Then we have defined different proposals. This is in order to identify the DCC dependencies into the calibration process. So I'm going to make a zoom because it's very small. Sorry for that. We have the processes, for example, the calibration, we go through the calibration implementing LabVIEW and Excel. So this is the steps in order to have the certificate. So we prepare the accelerometer ready for calibration, we prepare the signal conditioner, we have the signals into the data acquisition card, we have the data acquisition with LabVIEW. We have all the calibration data, the clients, the brand, the model, serial number, internal register, temperature, and relative humidity for iterations. Sorry for that. We have 10 records of each one of the electrical voltage, frequency, and total harmonic distortion. We have statistical data of the measurements. We have additional readings with different masses, vibration frequency, and or amplitude setting of the accelerometer calibration. And then we load this data into Excel to make some calculation of the uncertainties. And then we are expecting to generate the DCC through the Excel. This is one proposal. For sure, we need to understand the dependencies. The dependencies are, for example, we have LabVIEW and we get the information in an automated way, and then we send to Excel. But we need to, in order to define the uncertainty, we need to read the information from the calibration certificate of the accelerometer or our standard accelerometer. So this information is in a PDF. So right now we are copying the information and placing in a document that is our source in Excel, and then make some calculations. And this kind of steps are repeating with, for example, for the amplifier pattern and the acquisition data acquisition card. So we extract this information from PDFs, and this is not the best way to do the things. So the thing that we are trying to improve is to send from the PDF, generate an XML and read the information from Excel, read the information from the XML into the Excel. And in this way, we are going to have pilot digital calibration certificates of these different standards. For example, for the accelerometer, for the conditioner, and the data acquisition card. In this way, we have this first proposal that includes LabVIEW, Excel, and then we generate from Excel the XML for the digital calibration certificate. The proposal number 2 is, I'm not going to explain all the things again.
explicar todo.
Only I'm going to say that
Solamente voy a
we have a
decir
lab view to data acquisition. We
tenemos
process the information
la
in
adquisición de
Excel,
datos,
and then we generate the
lo
digital calibration
procesamos en
certificate
Excel
scheme in lab view.
y lo
And
procesamos
the
en
third,
Lambda.
well, this is more or less how we think to create a middleware in order to have the Excel information and generate the XML. But the proposal number 3 is improve all of these process, the calculation of uncertainties, the data acquisition, and the generation of the DCC using LabVIEW only. So in this way, we have full automate process. We don't have middlewares, and if you can see, the process can be simplified. So I know that this is the best way, but as a team, as a development team, we don't define this kind of proposal. We are not going, right now, we are not going to perform this proposal number 3. We are going to develop, sorry, the proposal number 2, because we want to learn how to use Excel in order to improve this methodology to other kind of services inside the laboratory, because the principal software that we use to generate and the process the information is Excel. So we want to replicate this to every service in the laboratory and maybe in CENAM. So that's why we are going to use proposal number 2, because covers not only LabVIEW, they are using Excel, and we want to propagate this kind of methodology in our laboratories. So that's why we select the proposal number 2. That's why this is an indicator of a crown, because this is the selected one. And then only to finish my presentation, we are going to propose a good practice for the quantity of the alternating acceleration, because right now there are only good practices in temperature and maybe later in pressure and humidity, but we want to share this at the end of the year, our proposed good practices in this quantity, and we expect to have a pilot DCC at the end of this year, so it's a work in progress. And the concluding remarks is that this is an effort that implies a multidisciplinary development. We are going to focus on developments that can be replicated to move services and not just one, and focus on services that can impact the final users or our users and our colleagues. So thank you very much for your attention. This, I think there is no question right now, maybe for the final stage. Thank you very much for your attention, and thank you again.
Aldo, muchísimas gracias por esta presentación.
Aldo, thank you very much for your presentation, and thank you for having developed this project. So now the next person will be talking about calibrations with BTs at volume. So this is going to be Giovanni Cepeda. He's an industrial engineer with experience as a business development representative in IT, petroleum and gas. And this is for Latin America, Europe, the Middle East, Africa, and Asia Pacific. He's worked in various companies such as Nestle, Dell in Mexico, at Box, Brazil, and he's currently working in Plim SP in Poland. So thank you, Giovanni, for being here with us today. And well, you have the floor. Welcome, Giovanni.
Oh, hi. Hi, everyone. Thank you so much for the invitation. So I will go quickly. Thanks for the introduction. My name is Giovanni Cepeda. I work in the oil and gas segment, mainly for the metering part, okay? So I work for a company that is called Plum. It's a Polish producer. And the topic today is about how we calibrate one of our star products, which is electronic volume correctors. In the Americas, it's called sometimes flow computers. But just for those not involved exactly in the oil and gas business, I will explain quickly. So in the world, to build industrial and commercial clients, the gas companies have to measure the volume. But the problem with the volume of gas is that at different pressure and temperature, the volume changes. So imagine if the volume is changing and it has to be built, then it has to be controlled, and it has to be measured at a specific pressure and temperature, so you can build the customer on their base conditions. So that's the reason in a metering station in an oil and gas, you always have a gas meter, which, for example, if you have a metering of water or of electricity, only the meter is enough. But for the gas, you need the meter to have the volume at measurement conditions. And then you need to have this device that I'm talking about, which is the electronic volume corrector. So basically, the electronic volume corrector takes a base pressure and a base temperature and calculates the volume at a specific base standards, so the gas company can bill the final user, okay? So this pressure and temperature changing of the volume is called ideal gas law. And these devices are called PTZ, which is base pressure, base temperature, and then we have a gas compressibility, which is an algorithm designed by the American Gas Association, which is basically the gases, natural gas. I'm talking about natural gas, which is about 60 PCI, which is around 4.1 bar, has a non-ideal behavior. So to compensate this non-ideal behavior, the compressibility factor has to be calculated. This is a standard already developed by the American Gas Association. The importance of this, as I mentioned, you have here a formula which is on the green background, and it's VB equals Vn multiplied by C. So the Vm is given by the gas meter, and the C, which is the correction factor, is given by the EVC, electronic volume corrector. And then this gives the actual volume that is going to be billed to the customer. That's why it's so important that these devices has to be very, very, very well calibrated, because it's directly involved in how much money the customer will pay. So we, as a Polish producer that belong to the member states of the European Union, we have to comply with the European Commission standards. We have basically two types of certifications, which is for the product, for the model, which is MID Module B. And then we also have another certificate for the manufacturing process, which is MID Module D. The MID Module B was given to us by PTV Germany. It took us a lot of time because of the restrictions and the metrological levels that we have to achieve in our devices to have this type of module be provided directly by PTV. On the right side, we have the max. That's how the accuracy levels are managed here. It is described as the maximal permissible error for pressure measurements and maximal permissible error for the temperature. So you have the left column and the right column. On the left column, it says 20 Celsius degrees. This is, let's call it the reference temperature. And then you have from minus 25 to 70 Celsius. And this is talking about the gas temperature. I'm not talking about the ambient temperature. I'm talking about the gas temperature, okay? And then you have here the percentage of these deviations that we have to achieve in order to be compliant with with the standard EN 12405, which is described here. This EN 12405 is the master of everything. Of course, this is provided by the European Union Commission. We just follow it. We just produce and have to follow this standard. We didn't invent it. And then this is for pressure and temperature, which is a measurement value. And then we have the correction factor. The correction factor is basically the final result that I explained in the previous slide, which is the result, the correction factor that is going to be multiplied, and it's going to give the final volume that is going to be billed to the customers, right? So this final result, as the EN 12405-1 describes, is 0.1% at reference conditions and 1% at nominal operating conditions. This is what we have to comply. This is the minimum requirements. Of course, every producer can have way better accuracy levels depending on the capacity of the calibration laboratories that everyone has. But this is just the minimum standards that you have to comply if you want to sell electronic volume correctors within the European Union market. How we validate this, how we can prove the customers that we comply with this, then we have we need to perform a report of conformity test. Now what I'm going to explain is just the way we do it, which is fully digitalized. We started doing this type of tests in 1987, 86. And of course, this has some, in the beginning, we used to do it on paper by hand. Of course, step by step and year by year, we managed to start investing more and more in technology so we can digitalize the whole production process because of the requirements of production. So I'm gonna just explain this quickly. It's to be honest, it's not difficult. It's the report of conformity test follows the EN 12405, as I explained, and a particular section 8.1.4.2. Okay, and you have the table 8.1. Okay, and you have here some T-min, T-max, T, and P-min. So basically, as you can see, those are 15 points. Okay, so basically, we perform tests in 15 different measurement points. Okay, so and then you have on your right 3 columns, and then the one that is highlighted in red, it says conversion factor C. Okay, so then you have reference values, you have indication of tested device. So the reference values, of course, these are the devices we use to compare. The devices that provide us with the temperature and the pressure, those are calibrated in also another laboratory we have, which is certified by ISO EEC 17025, which is in compliance with ELAC. Okay, and this laboratory has certification for temperature and pressure. So all the devices we use to compare are certified or are checked in this laboratory, which has traceability worldwide. Okay, and then the conversion factor, which is the volume correction. This is given by a program that we designed that is called METER. So basically, this is like the volume correction in one system that we use as a reference, okay? Because we don't really, for us, what really matters is the final result. And the final result is going to be always the conversion factor, okay? The temperature and the pressure, we don't sell it as a separate instruments. They belong to one equipment that is called Electronic Volume Corrector. And that's why for us, what really matters, it's the conversion factor. So, and then you have on the right in purple, indication of the tested device. This is the devices themselves, the model of the devices that it's the object of the test. So then we have the comparison, okay? And then on the next column, which is in green, you have the error and the uncertainty of the measurement, okay? So once this is explained, you can see there are 14 lines. So in every line, we check the conversion factor. And in the 0.8, which is in the middle of the table 8.1, in the 0.8, we, apart from checking the conversion factor as a result, we also check the result of the whole formula, which is VV equals to Vn multiplied by C. And then we also check, we make a comparison of the volume, which is called a volume at base condition, that is given by our system as a reference value against the indication of the tested device. And then we check the error, okay? So 14 points to check the conversion factor and 1 point to check the volume at base conditions result. And this has to be done exactly in the 0.8. This is how it's described by the section A142 in the standard that is the master of all of this, which is the 12405. Okay. So we have here on the bottom right part, in the corner, we have the results. Okay. And then, as I explained before, everything is measured in the maximum error. Okay. So you have to be, this is the minimum. And the European Union Commission is like, okay, you want to sell your devices in European Union, these are the minimum requirements. It has to be, this is the maximum percentage of deviation. So for the first one, which is the conversion factor, for this specific device, that is type MACBAT5 serial number, which is of course for every certificate, there is a serial number. We have, for example, for this particular device, the result was 0.02%. Okay, so it's way much less than 0.5. Okay, so way much better. So it's in compliance. And then you have the error of the volume, which is the 0.8. Okay, which is 0.01, which is of course less than 0.5. Again, it's way much better. It's in compliance. For EN 12405, these are the two values that has to be checked. Then the pressure and temperature can also be checked against. So you have the minimum requirements of deviation, and then you have what the report of conformity test is given. Some gas companies not only require the deviation of the final result, but also the deviation of the pressure and temperature measurement. Okay, even if those are not sold as a separate instruments, because they belong to one specific device, which is, as a whole device, it's the EVC, which is usually called for the abbreviation of Electronic Volume Corrector or flow computer. So once this explained, the errors, you have some formulas there just to calculate the errors, okay? Okay, so once it's explained this report of conformity test, how we do it. So we have a calibration bench, just like the gas meters have a calibration bench when you can test them and you can check the deviations and so on. So also for volume correctors, there are a calibration bench. So we have this one that it's where we perform all our tests, not only for our own devices, but also for different brands. So it's a multi-level rack, which can have capacity up to 50 units, 25 in each side. We have a thermostat for the temperature, which also it's capable of supporting 50 temperature sensors. Then for the pressure generation, we have a compressor and a vacuum pump. Then for the simulation of gas flow, of course, we don't use gas or we don't use air to simulate it. We just use a pulse generator. So the pulse generator, every pulse equals to a specific number of cubic meters. So then it's just basically a gas flow simulation, but electrically by pulse generation. Then we have an RS-485 serial connection, which control for every device, every single volume corrector has RS-485 serial connection that goes to a central system. This central system then has a serial connection and can send to all the devices the specific configuration for the test, okay? So basically the system is already prepared. You just click the button, sends the configuration to all the devices, and that's it. You can configure the gas composition of the natural gas, the algorithm, the minimum pressure range, the maximum, also for temperature, and so on. It doesn't have to be manually. Before we used to do it manually on every single device. Now we just mount it, serial connection, RS-485 from the computer, boom, everything is preset. This software, which is of course proprietary software, it's called MIDER. It's a licensed software, and it has the automatic generation of digital calibration certificates. So basically it just compares the reference values against the devices, that up to 50 devices, and says, okay, it's in compliance or not. If it's not in compliance, then it has to be double checked. If it's in compliance, then the automatic generation of a calibration certificate is done, is printed, and is put on the device, and it's sent to the warehouse. Of course, the room is air-conditioned room, which we try to have conditions between 22 and 23. And the relative humidity, okay, which is also for this specific test was between 37 and 50%. This is the capacity, and also complies with the recommendation, is a recommendation of WellMake 11.1, which is the module D for the manufacturing process, which is BMC. You have here some letters that says BMC. It has to be less than one third of the maximum permissible error. So this BMC is the best measurement capacity, and also we have to comply with we comply with this recommendation as well for the for all the testing that we perform on the devices. If it's not in compliance, then we have to double check the pressure sensor or the temperature sensor, and if it doesn't pass the test, then it cannot be sent to the warehouse, and consequently it cannot be sent to the customer. It has to pass the test. These are some photos of the thermostat, for example. You can see all the temperature sensors from the electronic volume corrector going to the thermostat. Then we have the modular pressure controller, also for controlling the pressure according to the pressure range that the pressure on the pressure sensor on the devices is installed, because those devices have different pressure ranges depending on the pressure of the pipeline, and we have capacity to calibrate up to 100 bar. Then the flow simulation. Well, this thermostat and the modular pressure controller, of course, you can see the brands there. We don't produce it. The flow simulation, we produce it. This is also something we developed. Basically, this can produce low frequency pulses, high frequency pulses. Also, we have some particular encoders that specific brands of gas meters from Germany use, like Namur or SCR encoders, also can be replicated or simulated in this generator. And this is the software that I told you, which is the mastermind of all of this process to make it digitalized and to do it quickly. So it's, of course, reading of the reference devices, checking the stability of the pressure and temperature, adjustment of correctors. That's what I told you by the serial connection. So all the correctors are adjusted by just clicking one button. The execution of the volume correction on the meter, on the software. Then we have the reading of the corrector values, pressure, temperature, correction factor, etc. And then it just compares and checks the calculation of the errors and uncertainties, and based on this, following the standard EN 12405, it will say if it's conforming or non-conforming classification. When it's non-conforming, it's highlighted in red, and then this has to be double checked. For the ones highlighted in green, it's automatically generates the calibration certificates. It's a stamp, sign, and that's it. All this test is done unattended. It means no supervision during the test, during the pulse simulation, the flow simulation. And currently we have, we started with one station, one workstation. Now we have 3 workstations, which give us a total capacity of 150 devices per shift for calibration. So it's great. Probably we will have to extend this. I hope so. But yes, this has come out of the necessity to have quicker delivery times. And then, of course, we cannot spend much time doing calibration. So it has to be the quicker, the better. And then the digitalization is important. This is the final report, which is the report of conformity test, which is generated if it's in compliance. And it's what I have explained you. Just provides the full information of the MACPAD5 device per serial number. It also describes the serial number of the sensors, the program version that it's on that specific device. Describes the gas composition that was used. We use full gas composition, okay, of the natural gas, which is called AGA-A, detailed composition, which is provided by AGA, American Gas Association. And this is mainly the report. So in addition to this, for statistical control, for statistics, we also test, we have specific chambers, temperature chambers, where 10% of the production we take, we put in these chambers to test how the device works in different ambient temperatures. I'm not talking about the gas temperature, I'm talking about the ambient temperature, because sometimes you have very hot countries where it can reach up to 50, 60 Celsius, or it can be very cold, like -20, -30. So you can check this, the range of the ambient temperature in specific chambers. So we can verify that the metrological test is in compliance, even if in all the range of the ambient temperature, okay? So not just in 20 Celsius degrees, but we check it also from -25 to 70. And this, we take 10% out of the production just for the statistical control of how it behaves. This is very important to highlight. We have the maximum time limit in years to carry out the sub-verification process. What it means. So after these specific years, the law tells you, okay, you have to take this electronic volume corrector, send it to a calibration laboratory, and perform the test again, just to validate that the metrological properties are kept, okay? Which is the sub-verification. In Poland, the law is given by 10 years. Canada is 7 years, Spain 4 years, and in LATAM, that's something that has to be improved, because so far there has to be some regulations with demand the sub-verification, so these metrological properties can be kept. And well, if you have further information, you have the reference there as well.
Tenemos la referencia ahí también si necesitan más información.
And well, that's all from my side. you have here the contact of our laboratory, which is the email. And I hope it was fun, this presentation, and thank you so much. Have a lovely day.
Muchísimas gracias, Giovanni, por esta magnífica presentación y por
Thank you, Giovanni, for this magnificent presentation and for having participated in this conference on digital transformation in metrology. I'd like to remind you that the questions for each of the panelists, you can enter them in the chat. Remember to also indicate the name of the person the question's for. Now I'd like to present Cristian Murcio, who will speak about Metrology 4.0, predictive maintenance in the industry. Cristian Murcio graduated as a chemical engineer in 2006 and a PhD in engineering in 2016, both from the University of Buenos Aires, and a master's degree on strategic and technological direction from the Technology Institute of Buenos Aires in 2022. Since 2006, he's been working for High-Tech SRL and is now manager of research and development. He has carried out different work developing different measurement equipment in physical variables and the integration of platforms for predictive maintenance and optimization of processes using artificial intelligence, as well as equipment based on NIR spectrometry and the detection of the product concentration, and for equipment online to detect color and concentration. He also participated in research projects financed by ANR, and it's a privilege to have Cristian Murcio's participation. The floor is yours, Cristian. Hello, good morning. Can you hear me? Yes, we can, Cristian, and we can see your presentation too. Well, thank you. Just a second. First of all, good morning, everybody, and thank you for having invited me to participate in this session on metrology for digital transformation. It's a pleasure for me to be able to talk about my experience in the technology for 4.0, and also to speak about what we've been doing together with INTI in order to integrate DCC into the value chain. So in this presentation, then, where I'm going to introduce the measurement system for predictive maintenance that we develop in the context of 4.0, and its relation to current metrology. The agenda also includes a presentation, a brief one on the company, and then the development of hardware and software and their integration with the digital calibration certificates and the impact that we expect for the final user. So I'm going to start to summarize what we do in High-Tech. We're a company that was founded over 30 years ago, and we provide technological solutions for adding value to products through measurement and analysis of the different parameters in the process. Since the beginning, High-Tech has focused a lot on the research and development of measurement equipment, and in the last 15 years, we have a formal department, and I'm the person responsible there, and I've been able to focus resources on innovation, both at the level of hardware and of software. Right now, we have two research lines. One is a traditional one for massive industrial measurements based on the interaction, and another research based on 4.0 industry research. And that's what we're going to focus on in this talk. A lot of these technologies that have been developed have been transferred to other areas where products for clients all over the world, and also our calibrations department, where we are developing technology related to DCC. So the metrology laboratory, this started at the beginning of the year 2000, and it is a strategic business area for us. And its existence basically is to, well, we're developing the DCC. After this brief presentation of high tech and what we do there, I wanted to refer briefly to what we understand by Industry 4.0. I'm sure a lot of you have heard about this concept. It originated in the creation of smart factories with more efficient, productive processes and focusing on quality too. Smart factories also have they're not just more efficient, but they have a better capacity to adapt and connect to the final user, receiving client feedback and making improving decision making to make it possible for people to work together with robots and artificial intelligence in order to take more rapid and better decisions. And through a smart connection with the machinery and processes based on certain technologies that make it possible to achieve this change of paradigm. We have global computing, Internet of Things, big data, and this new paradigm of connectivity is the capacity to acquire and analyze large volumes of data so that these technologies can transfer it into information and then knowledge and then decision-making capacity and the capacity to take action. Some of this has been mentioned in other talks, but veracity is a fundamental aspect. So DCC for 4.0 industry, we're thinking about the inclusion of the DCC in predictive maintenance and the types of smart maintenance. We have different types of maintenance. Corrective maintenance that's carried out when there are certain failures in the machinery. So we analyze where the failure is so that we can repair the equipment, or if it's more economic to replace the equipment. So if the cost of the equipment is very high, then we can correct the problem. And this is a strategy that we use. So predictive maintenance uses statistics and measurements and experience to determine the service interval for equipment and make sure that the maintenance of the equipment is done on time. So these strategies are evaluated based on certain indicators, the average time between failures, for example, and availability. And there are several advantages to this process. It facilitates understanding the origin of the problem. It increases accountability, eliminating human errors. It makes it possible also, in a case that we're going to talk about, is establish connection with the local network and issue warnings in remote plants, for example. So there are several advantages. So briefly, I'm going to show you the tool that we developed and how we are integrating this DCC into this tool. So here, this is somewhat simplified, this diagram, but this is how we integrate the technologies of Industry 4.0 and the Internet of Things, computers, artificial intelligence, and big data. So to develop the concept of predictive maintenance, we developed the hardware and the software, and we're preparing this ecosystem to include the DCC. The tool that we developed is made up of a platform in the cloud and sensors that we've designed to facilitate the access to data. These are third-party sensors. Hardware, because we need to acquire data, the data that we require with the frequency that we require them. And for example, data from 3 elements at the same time. The development of the platform on the cloud has several advantages, including the fact that we can manage the data that are generated, and this makes it easier to integrate the data from the sensors, and other advantages such as standardization, data protection, data security. And so we take advantage of the expertise of the suppliers or providers of these platforms to guarantee the data security, and also to prevent a cyber attack, which is a significant threat. It also allows the simple integration with the tools and reduces the possibility of human errors. And if we analyze the measurement chain, we have the data from the sensors, and that will result in the corresponding DCC. So it goes to the center, then has the process to the possibility of the capability of processing the data, and once processed, they're sent to the cloud, to the platform where the different algorithms will use the data, integrate them, analyze them, reach conclusions, and send notifications. We have developed several sensors, but this one is the one we use the most. It's a vibration sensor with several characteristics. As I said before, the possibility of obtaining data from the 3 axes or 3 areas at the same time, and also for preparing the sensor for field calibrations and verifications. We've had to design the sensor anchor so that for repeatable reinstallation relative to the sensor orientation, because this has a significant effect on the values measured. So we had to develop a part so that we could repeat this process. And also, without talking too much about the technical aspect, we do send the data to the cloud using an acquisitor, and so that we can encrypt the data and incorporate a large amount of data, a large amount of information, and so that we can take advantage of the use of resources. And also data veracity is an important element. So we take advantage of the computing capability, edge computing capability. So this equipment has different characteristics. It was designed and tested specifically to support industrial use. We tested it with electrostatic tests. And the interesting thing is to be able to see these sensors, that they can be used not only all together. We can see a pump and a motor here, and this is a whole system, and we start to combine information from the system and use a manual analyzer for making comparisons between the measurements, as you can see on the right. The last stage in this chain is the platform, the cloud-based platform. This processes acquires the data, processes them, and this structure sends the data to the cloud, and the data in the cloud are again analyzed and classified. The use of the data and the algorithms adds value to the final user. Normally, the users don't have this knowledge about evaluating the data. So what the platform does is that it guides autonomously the data analysis and produces notifications, warnings, and corresponding reports. The inclusion of information on uncertainty in these data that are generated and the effect of these uncertainties and the results of the algorithms are of fundamental importance so that final users can reach conclusions that are or that have value. This is our interest. Our interest is to incorporate DCC into this chain. Also, when we investigate the effects of uncertainty on the failure diagnosis. So what is the value for the client? Well, the information that we submit to the client for decision-making and for executing actions is the information about the active status as well as the evolution of assets. So the platform has different screens, including this one here, which is a dashboard that shows us the status of the assets. And we can detect a condition of the asset that doesn't go beyond certain limits. Also, the platform can detect anomalies or anything that is unusual, not necessarily a failure, but a situation that needs to be evaluated. Another significant information is the evolution of assets. We can analyze the previous periods. So we've got the last 5 periods to see the variables. In this case, the vibration, which has been varying during recent periods, or it detects the very low or the worst periods. We can see the vibration axis here and the limits. Also, the platform includes screens that are useful for users so that we can see historical data. Here we can see the spectrogram based on time, also so that users who have more knowledge and want to carry out their own evaluations, there's information here for them to do so. Here are other spectrograms. And here's a spectrum, a velocity spectrum, and the platform can distinguish the fundamental velocity, and this could be useful for the users. At the same time, the platform sends reports by email and warnings, but all of these reports and information have value regarding the veracity of data and uncertainty. So this predictive maintenance requires low-cost sensors and the need to use calibrated sensors. Right now, requirements are increasing, and as I said before, we are evaluating the effects of the conclusions. So the requirements, market requirements, go hand in hand with the need that we have to generate these data. This is why, together with INTI, we developed a project which will allow us to get data from the sensors and link these to the digital calibration certificates. Yesterday, we heard in one of the presentations the problems in Latin America for adopting technologies. We have the privilege to implement this project that allows us an SME to adopt these services within the Industry 4.0 framework. So the platform that's developed on the cloud will receive and use the information related to DCCs. The calibration system that we're developing will make it possible to issue these certificates using different commercial calibration instruments. The impact that we hope to achieve with this in the value chain for the final user. Well, the idea is that INTI would calibrate our main instrument, and then the secondary standard, and then the sensors. The value that we propose to the client is, first of all, to guarantee traceable measurements in also the possibility of interchangeable sensors. And finally, to acquire knowledge of measurement uncertainty to guarantee the veracity of the data and improve the predictions through the results of by improving the algorithms. So we used a reference sensor. This is and also a secondary pattern. How are we going to do this? Quickly, the idea is to control the secondary pattern in order to achieve the calibration conditions that we require. And once we have the data from the sensor to generate DCC to the cloud, and this information will remain in the cloud, and it will allow us to use it for data analysis the data generated by the sensor. So this is a summarized diagram related to the generation and storage of the DCC. We have the data, the traceability, and through an application, you generate the package containing the DCC and a certificate that's legible by people. This can be saved in the cloud and downloaded by people, or so that data can be analyzed. This is another instrument, a field vibration verification instrument. And we are thinking here of using the DCC structure to record the background or previous data. So what is the status of the project currently? Right now, the DCC can be issued. We need to do additional work to adapt the whole platform. Regarding primary standards, we've acquired the equipment and we're developing the procedures. And finally, the platform, well, the sensors require adaptation for using DCC, hardware adaptation to adapt them to the calibration system. And we hope that by the first half of next year, this project will be concluded and operational. So this was a summary of the way that they're working to incorporate DCC for predictive maintenance for 4.0 industry, and the way that we're thinking of integrating DCC to add value for users. Thank you again for your invitation to participate and for listening to my presentation. Thank you. Thank you very much, Christian. It was a very interesting talk, and thank you for having shared this information with all of the participants. Let's start with the question and answer session. And also in following question and answer sessions, you can enter your question in the chat. As we said at the beginning, then Rubén Gil will support us with this. Thank you again, Rubén, for your participation. Thank you. Before starting this block, I'd like to thank you all for your excellent presentations, Aldo, Giovanni, and Christian. And in fact, it's true that topics related to DCC have been mentioned, and also 4.0 industry. And one of the presentations addressed a measurement with a digital component. and everything is based on digitalization, automation, and getting these additional applications. So thank you for having shared your experiences all. So let's start with the questions and answers. I have one for Aldo. What do you consider are the main challenges that a laboratory faces in order to change from analogic certificates to digital certificates? Thank you very much. First of all, one of the challenges that I've seen is, first of all, to accept that we have to establish a position related to the implementation of digital certificates and decide where we're heading and what our goal is for issuing these. And secondly, to get down to work and make the analysis and take the steps that I mentioned in the presentation. This is multidisciplinary work, and it's not just a question of including metrologists, but also a work team, as we've seen in the different presentations. It's work that involves many different people and collaboration between companies even, and organizations too. So I think that is the challenge, to find partners and make decisions as to the direction we're heading in, and to start to work in a coordinated way to achieve the objective, which is to issue digital certificates. That would be my answer. Thank you, Aldo. The next question is for Giovanni. The question says, under which platform can you read the sensors, or if this platform is a commercial one that's been developed by a company? Well, of course, this platform is MEDER. It's a platform developed by a company called Plume. And basically, it's the platform that obtains the data from the sensors, both on pressure and temperature, the calculation of the volume based on the standard, and it's compared with the devices that are subject to testing. But all of this has been developed by the brand Plume. Thank you, Giovanni. The next question is for Christian. What type of service on the cloud do you use for data analysis? Is it a commercial cloud? Is it significant, this requirement, or the bandwidth requirement required for this type of application? Well, in the cloud, we use data capture services and storage and visualization services. The algorithms for processing, we develop those ourselves. And regarding which cloud, we use the Google platform because we're partners with them. And so we have professionals who are certified in the use of this tool, this platform. Regarding the requirements for bandwidth, it would be significant if we didn't carry out this type of processing, as we mentioned in my presentation. With the edge processing, we have 90% of the data, and so we can get the most valuable information, so we can reduce the bandwidth considerably in this way, through this process. Thank you, Christian. And also taking advantage of the fact that you're there, the last question, can you let us know what structure considered for the DCC? Does this belong to the developers? We are considering an original structure of the PTB to try to make it as standardized as possible. I'm not sure what the second part of the question means, but this is the original structure that we are taking into account. With what you're saying, that it's under the PTB structure, then that helps a great deal to understand. So thank you. Thank you, everyone, for your questions, and mainly Aldo, Giovanni, and Christian for your presentations. So thank you all, and go ahead, Germán.
Thank you, Rubén, and everyone else for having conducted this Q&A session, and thank you to the panelists for their presentations. So with this, we'd like to end the first section of today's meeting. We would now like to move on to our break, but before that, I'd like to ask everybody to turn on their cameras so as to take a screenshot. So we'd like to ask Francisco to let us know when the photograph will be taken and when we'll be going on to the 10-minute break. Thank you, Germán. So we have 129 attendees on Zoom. So I'd like to ask everyone to turn on their cameras so that we can see most of the participants. So it's a little bit complicated because some people weren't ready to turn on their cameras. So I'd like to ask them to turn them on if they can. And please give me just a moment because we have several screens we need to take screenshots of. So give me just a moment and we'll begin. Please smile. Let's take the first screenshot. One moment more.
Muchas gracias. Voy a la mitad, un poquito más, por favor.
I am halfway through, so just a moment more, please.
Pues agradezco a todos los que pudieron encender su cámara.
So I'd like to thank all of those who turned their cameras on, and we've finished taking the screenshots. Thank you, Francisco, and thank you everybody else for having participated. So you can now turn off your cameras and we will now take a break, and in order to be able to finish on time, we will be coming back at 16:40. So when we come back, we'll be talking about artificial intelligence and its implementation in the metrology environment. So we'll have a few presentations. So we'll be back at 16:40. We'll see you back here soon.
Welcome back, everyone. Now I present the last block of the day that deals with artificial intelligence and its application in metrology. For this topic, we are joined by James Fitchak, who will support with the moderation of the Q&A block. James Fitchak received his PhD in experimental atomic and molecular physics from the College of William and Mary in Virginia in 1994. And he joined the National Institute of Standard and Technology NIST of USA in 2003. He briefly worked in the photonics industry after holding postdoc position at Argonne National Laboratory, developing spin polarized deuterium targets for nuclear collision experiments. And at the University of Wisconsin, studying ion spectroscopy related to laboratory astrophysics. Between 2007 and 2019, he led the vacuum project at NIST, where he worked to modernize NIST calibration service in low gas flow and vacuum gauges, and launched a program to build a cold atom vacuum standard. He participates in the Consultative Committee for Mass and Related Quantities working group on pressure and vacuum of the Bureau International de Poids et Mesures by APM. In 2019, he took a new role at NIST as the Associate Director for Measurement Service and has become involved in the worldwide effort for the digital transformation of metrology, representing NIST on the SIM Technical Committee for the Digital Transformation of Metrology, M-MWG14 M4DT, and the IMECO Technical Committee for Digitalization. Thank you, Dr. Fitchak, for joining us today and supporting us with the question and answer block of this topic. For our first participation, don't forget that you can ask your question in the chat during the presentation, and at the end, the speakers will answer all the questions for the social network and from this Zoom platform. We would like to inform you that due to time constraint, we have shortened our speaker resumes, but we want you to visit the events webpage where you can obtain more information about each one of them. Now, I'm pleased to introduce Dr. Gilad Kuznin, who will be giving a presentation entitled Fundamental of Earth-Changing Measurement Science. Dr. Gilad Kuznin received his BS, MC, and PhD degrees from Carnegie Mellon University. His staff is scientist with the National Institute of Standards and Technology NIST in Gainesville, Maryland, an adjunct professor with the University of Maryland, and a fellow of the American Physical Society. His research is part of the White House Material Genome Initiative at NIST, a project which aims to accelerate the discovery and optimization of advanced materials. He leads the machine learning team of an international cross-disciplinary effort building autonomous research systems with the goal of advancing solid state, soft, and biological materials. For these systems, machine learning performed experiment design, execution, and analysis. For his work, he has been awarded the NIST Bronze Award. He is also the lead founder and organizer of the annual Machine Learning for Material Research Bootcamp and Workshop, educating next generation and mid-career material scientists in machine learning. Go ahead, Dr. Gilad Kuz, with your presentation.
Okay, thank you. Let's see, share screen. I think this is the slide. Yeah, all right. Can you see my slides?
Yeah, yes, we can see that. It's okay, Doctor.
All right, okay, great. Yeah, so I'm going to briefly with the amount of time available, I'm going to briefly talk about autonomous metrology. So this is where machine learning guides which experiment to do, which measurement to do, how to do the measurement, how long to do the measurement, all those types of things. Autonomous metrology is basically the union of of AI machine learning and measurement science. Traditional measurement science, you're interested in a point value or potentially a vector or an image at some point location with a set of parameters that you've chosen before. So that's your measurand. That's the thing you're trying to measure. And then you have some level of uncertainty associated with that measurement. So for instance, if we're interested in measuring the height of this film at this location, we get a height plus some level of uncertainty associated with that. So autonomous metrology or autonomous measurements, instead what we're trying to do is we're not trying to just measure that point, we're trying to measure the function that describes the surface. We're trying to actually measure the underlying function. So here our measurand is the function, and the uncertainty, instead of just an uncertainty in a point measurement, we have an uncertainty in a function. So this set of functions. So here in this previous example, we're measuring just one point. Here we're measuring a function. So each of these curves here is an example function which could be the function that you're measuring, and this blue region here indicates the uncertainty associated with the function after you've done some measurements. So it turns out, so not all possible functions are realizable in the lab. So when you're doing autonomous measurements, if you're just using machine learning to guide your measurements, just black box machine learning, it will suggest all possible solutions. And that most of those solutions are non-realizable in the lab. So for instance, if you're doing an X-ray diffraction measurement or a Raman measurement, you know that you shouldn't get negative values in your measurement. The intensity value shouldn't come back negative. So we can impose those types of constraints of the measurement. So if you're doing electron microscopy, you can encode the prior knowledge, the prior physics of an electron microscope into your machine learning, which is guiding your selection of which experiment to do next. You can encode the prior knowledge of X-ray diffraction or Raman or whatever measurement tool you're using. So you can encode that into the machine learning, which is guiding the measurements. Also, the thing that you're studying will have some restrictions on that as well. So for instance, you may be studying a certain material with a certain level of smoothness, and you have a sense as to what range of smoothness it could have. So you could also impose that as a constraint. And I'll give some examples in a few slides on these types of constraints. So based on this, if this is one function that we could be measuring out of a large set of functions that we're measuring, and this is the space of all possible functions. So if we encode these rules of the measurement tool and the thing that we're measuring, it will subselect a smaller region of possible functions. So we go from all of these possible functions to a subselection of functions. And then on top of that, we have, once we collect data, there's an even greater subselection of functions that agree both with the physics and the data. So the main point here, so here's an example. So let's say, again, we're studying the topology of some sample. So we can have functions that are smooth and so they're smooth, but they vary very quickly in the direction X. We can have sharp transitions or slowly varying functions. We can have alternatively smooth functions that are very slow varying. So these are three possible classes of functions that could describe the topology of this material. Maybe you have prior knowledge about the topology, so you could say, well, only this set is viable. So you can include that into your machine learning using constraint programming or probabilistic constraints, probabilistic priors. And then on top of that, you can encode your measurement constraints. So for instance, if we know that the height of the material can only be positive, we can restrict our functions to just the ones that are positive. Another way to think about this is we're not just measuring the function of the surface of this material, we're actually choosing a hypothesis of how the surface height changes. So you can think of this as we're actually searching through space, through hypothesis space, for the best hypothesis that explains the thing that we're studying. So again, instead of normal metrology, we're interested in making point measurements or spectral measurements at a point or image measurements at a point. But here, what we're really trying to do is we're trying to actually measure the hypotheses. We're trying to sub-select and pick the best set of hypotheses that best describe our challenge. And so this whole thing is done using active learning. It's a subsection of, it's a field of machine learning that's dedicated to optimal experiment design, and more specifically for getting maximal knowledge of an underlying hypothesis. So active learning is the field of machine learning, which is most important for this. So an example is shown here where we have a red data point, which is drawn from this hidden red curve. We have this hidden red function, which we don't have information for. We then fit it with a probabilistic model, like a Gaussian process. And so then this black curve here is the estimate of what the machine learning algorithm thinks the function is, because it only has this one data point. What you can see is, so this gray region is the uncertainty. So it has greater uncertainty as we get away from the data point and lower uncertainty when we're close to the data point. So then based on the model expectation, so this black curve where it thinks the model is, and where it thinks the function is, and its uncertainty, we can then guide the selection of new data points, new measurements, which can best narrow in on the correct response. You can see within a few data points, we're able to converge to a pretty good solution of what that function was, or what the correct hypothesis is for explaining the thing that we're interested in. So there are many methods for doing this. The simplest method is you just look for where you have greatest uncertainty and you measure there. That type of method is highly local, and it only cares about local information. You can get more global information about the entire function that you're trying to optimize by using a subset of methods called look-ahead methods. An example being risk minimization. In this case, what you're doing is you're saying, if I were to do any of these possible experiments, which experiment would provide me the best knowledge, the most knowledge for making subsequent decisions. So this is look ahead. So you're looking at the possibility of all possible experiments and choosing the one that would give you the best bang for your buck. You can also, there's also another subset of methods called Bayesian optimization methods. And this is where you're not just trying to figure out what the function is, what the hypothesis is, but you actually have some set goal that you're driven towards. So for instance, you may want to find on your surface of your sample, you might want to find the point that's the highest. So that would be your objective. And there's a way to encode that objective and then use machine learning to help guide you towards that objective, towards finding that extrema of your objective. So that's a brief introduction to the basic ideas of autonomous metrology. So again, the whole point is to instead of trying to study one point at a time, we're actually trying to learn the underlying function. So that the goal of autonomous metrology is trying to learn to pick the best hypothesis that explains the thing that we're studying. And if you're interested in learning more about this, we have a course, a 1-week course, which we teach on introduction to machine learning from beginning to end, from intro to Python, all the way to how to design these algorithms. It just met a couple weeks ago, so the next one will be sometime in the summer of next year. And it's hybrid, so you can join online. And if you're interested, please either contact me or you can go to this link. And it's all hands-on. So I'm not sure how much time I have left, because I think, so I guess I have 5 minutes left maybe. In those 5 minutes, I was just going to give some examples of these types of things that we're doing at NIST. So in this case, we have a bunch of point samples on this wafer here. And each of these samples is a material made under different composition. And the goal here is, what we want to learn is we want to measure the phase map. So instead of just measuring the phase of each individual material on this wafer, we want to measure the entire phase map. The phase map is how does the structure change? How does phase change as a function of composition? And in this case, so the answer is shown. The answer that we're trying to learn is this. So this is the hypothesis, the correct hypothesis. And we can use machine learning, and it's controlling, in this case, a diffraction pattern, it's controlling an X-ray diffraction measurement system that's measuring point by point on this wafer over here and collecting data. So each of these dots is a sample on this wafer that we could measure. And the dark points are the samples that have been measured. And the black lines indicate a hypothesis. So here, it's saying that it thinks there's going to be a phase boundary here and here. The correct answer are shown here. These are where the correct phase boundaries are. And then the color coding is indicating uncertainty in the hypothesis that it's gotten. So in this case, it only has 3 data points. And what happens is it uses it looks ahead at all possible experiments it could do on this wafer and decides which one would provide the most information about this hypothesis, about this model that it's trying to learn. And then it selects that point, measures it, and then updates its prediction. So here you see we have new predictions as to where these boundaries are. This is one example. We've shown, if you're interested, that we have a paper demonstrating that the more physics you encode into the algorithm, the better performance you get. So here we have on the bottom axis the iteration number. So how many experiments have been done? And this is the performance of the algorithm. And each of these curves is a different level of physics being encoded. And as what you see is that the curves go up with the amount of physics encoded. In this case, we decided to extend this and actually try to use it to help us find a new material, a material that maximizes some property. So here we have the phase diagram, and the phase diagram is also related to the property, the magnetic property of this material, which is indicated by this color coding. And so what this algorithm is doing is so we've set an objective. We tell it we want to find a material with the best saturation magnetization, which is the yellow points over here. And so what it's doing is the machine learning is now doing autonomous metrology to understand the phase diagram shown on the left and exploit that to speed us up to find the best material. And so basically the argument here is that using autonomous metrology can actually help in doing things like materials discovery and materials optimization, and not just materials, but process optimization, process discovery. And as a result of using these types of methods, we were able to discover the first a best-in-class material a nanocomposite phase change memory material as a demonstration that this method is able to, using autonomous metrology, you can actually accelerate your research. We've done something similar for neutron scattering, where we're interested in learning about. We have a magnetic material. We stick it into a synchrotron, into a neutron scattering facility measurement site, and what we're interested in is figuring out what's the magnetic response to temperature of this material, and we can use autonomous metrology to most rapidly discover how that material behaves at different temperature, what its magnetic properties are at different temperature. And we can do this also for other things. So in this case, this is learning the phase diagram of a material over at different temperatures, different composition and temperature. And in this case, the machine learning has direct control over the physics and a simulation tool that encodes the physics of material phase of thermodynamics of phase development within material. So yeah, so that's all I have. So if you're interested in learning more about using machine learning to do science, please look us up for our boot camp. Yeah, I'm open for any questions if there are any.
Thank you very much, Dr. Gil Kuzny, for your excellent presentation and being part of this annual conference on digital transformation in technology. We are going to make some questions later.
Okay.
And now I present Rodrigo Felix, who will give us the lecture entitled Lung Ultrasound and Virtual Vector Machine as Meteorological Tool for Diagnosis of Acute Respiratory Distress Syndrome. Rodrigo Costa Felix has a PhD in Biomedical Engineering, 2005, working at Inmetro from Brazil since 1996. He is the lead of the Ultrasound Laboratory since its foundation in 2008. He's currently the professional development coordinator with this SIM. Rodrigo has supervised 28 master theses and 7 doctoral dissertations, and is the author of 82 peer-reviewed papers and more than 100 conference papers. Thank you, Dr. Rodrigo Felix, for being in this conference. Please go ahead. Dr. Costa, we can hear you. We can hear you, Doctor.
You need to check the options for the microphone.
Yes.
Now, can you hear me?
Yes, now we can hear you.
Right, great. So because I had some problem in the beginning of the communication, and so I tried to improve my audio, but I think that I did exactly the opposite. So just to be sure that now you can hear me first of all, and
we can hear you and your presentation also. Don't worry.
All right.
It's okay.
So it's not in the presentation mode yet. Now it is.
Right now it's in the presentation mode. Yes.
Great. Thank you so much. I apologize for that small delay, but I think that I will not taking that amount of time that was led to me to make this. But anyway, first of all, gentlemen, thank you so much for your introduction, and I would like also to thank Hugo Gasca, who actually invited me for here. I try to speak as slow as possible because I know I have some delay, and so that the translator Fiona is not easy to do the proper translation if I speak as fast as I typically do. So that's the title of my presentation today. It's a project that is supported by International Development Bank, Inter-American Development Bank, and the organizer of this project is the SIM. Okay, this project is conducted by 4 NMIs within SIM. I'm the coordinator, and we have other 3 NMIs with their respective contacts here. And also there are some researchers that take part on this project. And we start working with CENAM in Metro, for where I belong, INTI, CENAM Mexico, INTI Argentina, and East USA. So first of all, it's important to let you know what lung is. Lung ultrasound, of course, this image is just a joke because you don't usually put the probe of the ultrasound in the lung itself. Instead of that, you use, of course, over the skin of a patient, of a person. But the fact that this probe is able to make images from inside the body. That's what ultrasonography is. And if this image came from lung, so it's called loose or lung ultrasound. This is an image. Of course, I'm not a radiologist, I'm not an imagologist. So I know that it's lung because it's written here. But I know the principles that work behind this image, that how it's called, collected. But the fact is that lung ultrasound is that way. And how does it work actually? Not for lung ultrasound, of course, but for many different imaging diagnoses. What we do is to have, depending on the image, the characteristics of the image, you can make a score of the characteristics of that disease. In this case, as much bright is the image, the worse is the case of this disease that's called ARS, acute respiratory distress syndrome. So it's possible to make the scores based on LUS, and then to identify in which stage is the disease in that patient in particular. And acute respiratory distress syndrome, that's called ARDS, happens when the lungs become severely inflamed from an infection or injury. The inflammation causes fluid from nearby blood vessels. Of course, you know that the lung is full of blood vessels in its surroundings, so that it's possible to change the oxygen. The blood cells can change the dioxide of carbon with oxygen, so that it's clean, let's say, the blood with that in that way. And when for some reason this fluid in the nearby blood vessels leak into the thin air sacs in your lungs, then you can have difficulty for breathing, because it's quite similar to drop. I mean, it's similar to happen when a person get water into the lungs. And there are many diseases that can cause that. One of those, it's the driver for this project, was COVID. COVID is the disease, of course, you all know, the pandemic. For a long while we have it worldwide, and then it can cause ARDS in some circumstances. Actually, I must say that's very rare, but it's possible to happen. And what we can see here, look at pay attention that in this images are not from ultrasound, but they are high radiography. That means ionization radiation images, and you can see the appearance of healthy lung and a lung with ARDS in it. So that's what we have regarding the disease and the images we can get from that. And then virtual vector machine, what it is exactly what is related to. It's a supervised learning model with associated learning algorithm that analyze data for classification and regression analysis. Virtual vector machine is part of what we call generally as machine learning, which itself is part of what we call artificial intelligence. And this robot is quite intelligent, as you can see, because he's able to see, maybe to process all these equations and figures and so on. And that's an internet general imaging showing how these things, these concepts are connected. What we are talking about is exactly that way here. That means that is diagnostic. So the idea of this project is to use virtual vector machine to make the diagnostics of ARDS based on lung ultrasound. What's the reason for using exactly this kind of approach? Because LUS is widely used. It's basically easy to be used. Of course, in some countries there are necessity to have a professional certification. It depends on which country, but maybe usually is that the case. It's relatively low cost. Of course, if you compare with radiology, the cost of the price of the equipment is lower than radiography equipment typically. It's a no-ionizing radiation. Of course, that nowadays, since a long while, to have is quite easy to measure properly the dose of your ionizing radiation that is delivered to the patient. But even so, it's better to have, let's say, a way to inspect the body of a person without being necessary to worry about if it is being ionized or not. And another important point is that fact is that lung ultrasound, ultrasonography is quite easy to be tested in the point of care. That means where the patient is. It means in urgence center, emergency center, or even at home. Home care facilities is quite easy to be use this kind of equipment. And also we have already some studies that says that LUS have been successfully used to diagnose COVID in the early stage of its commitment to patients. And there are more than 1,000. I will just show you some results we have already on this review. There are more than 1,000 of papers that have been published recently regarding this approach. This systematic review is undergoing. I will show the results in a few slides more. So what we ask with this proposal, with this project, is LUS safe for ARDS diagnosis? Of course, that's partially responded by the project motivation, because it is, in fact, and it had been used for a while. And another question is this a proper metrological tool for ARDS diagnosis? That's what we would like mostly to confirm with this project, the outcome of this project. And another important question is, whose VVM improve the happiness of our diagnosis. Of course, it depends on the diagnosis accuracy. If not, of course, it will be worthless to use LUS for this purpose. In this case, what we are planning to do is a comparison between a human and a VVM analysis as part of the methodology. So we'll work on that. And our challenges are basically on metrology aspect, is to prove or evidentiate if LUS images are accurate, has accuracy enough to be checked. I mean, we will use LUS images and then check if they are accurate enough. And also if we will check if VVM has accuracy enough to check this different aspects of LUS images. Regarding technology, we'd like to make the link and validate it metrologically between LUS and ARS. And in the methodology aspect is to make available LUS images database to completeness to be checked. Those are our challenges in this project. And because of that, the main objective is to find out the applicability of VVM to help us on the diagnosis of ARS or DARS based on LUS images. And we have also some complementary objectives that are to find and check if LUS database for ARS are good enough in the web, if they are freely available, and then consider that we achieve these objectives. So we would like to retrieve a large amount of data regarding LUS and ARS to develop a VVM to categorize different LUS based on LUS images, and then to propose a tool to diagnose accurate respiratory syndrome, ARS, based on VVM. So we have as main objective, basically, DARS. And how are we planning to do that? First of all, we are looking for a database where LUS images are available for specifically this application. Then we will evaluate using some imaging processing to evaluate integrity and reliability of those database. And after that, we will develop a virtual machine to categorize LUS images with respect to DART, based on supervised tests and then accuracy check. And the proposal of this project is basically to develop and to offer an automated tool to diagnose ART based on different LUS score that will be technically validated, metrologically validated, and also free to use worldwide. Of course, industrial and intellectual properties to be well adjusted throughout the project, depending on the characteristics of each country that is taking part on this project. Another outcome that's we are looking for is to spread out acknowledgement of LUS, ARS, VVM among SIMs and MIs, doing that through technical exchange, doing that through internships, and also the idea is to make a culture or to improve the culturalization of metrology for digital transformation regarding ultrasound usefulness. Of course, there's much more to be exploited, but those are the main outcomes that we are willing to do or to provide with this project. Due to that, the expected impacts are better, faster, and more accurate diagnosis for ARS, and of course, basically based on a technical development project, to make as easy as possible the application of this tool or that tool that will be developed. Of course, metrology for digital transformation is a deep need to forthcoming entrepreneurship of metrology, added value investments. That means that we would like to make easy, to make clear for those who like to invest on metrology that M4DT is a good way to do that. I mean, we can call attention for investments, public for sure, but also private investments for this approach. And something that we are willing to do also is to use the point of care treatment viability with an additional value of metrology, because we have already, of course, many treatment, many approaches that are applied in point of care places, but metrology are sometimes not very well, say, considered on that fact. So the idea is to show up that metrology is good to be close to these applications. And we also like to make the circular and global economy improvement based on healthcare and health tech investments. And not at last but not least, better communication with the citizens regarding the metrology itself. Just to finish my presentation, we start on this project almost 1 year ago, 10 months ago, more or less. And we have some interaction so far with the group. We have forthcoming activities that are 5 internships to be arranged. And basically, we would like to have it from October this year until May next year. We have already 2 of them practically decided. And then a final meeting in which we will just join all this, the outcomes in a proper document that will be divulgated everywhere. And the project time span is that one here, and it will be ended in more or less 1 year from now. That's some figure regarding the expense. It's not that important, but anyway, it's here to mention. As I mentioned, we had already done some literature review. We are doing systematic literature review. We have so far fostered more than almost 1,000 papers. Actually, the first trial was almost 1,000. The second trial was almost 1,500 papers, and the third trial is to be done yet. But of course, all this is not true that all these papers are exactly related to the subject of this project. So we have about by now 260 papers to be reviewed, and this is the way we are doing that. And we have already review that will be published recently in the near future in a Brazilian Congress on biomedical engineering, and in the near future in a proper scientific paper. We had sorted out defined some bases that from which we will extract the images to be using this in this project. And there are other approaches to be done. And what is more important of all those that I mentioned is that we decide that some kind of simulation, numerical simulation, is also important. And one of the internships that we had already planned is close to be done is to make simulation with fields, and or wave to make tomographic and scattering data, and also the interchange that we had planned, I had already mentioned. So that's what I have to present to you today. Thank you so much once more. And as soon as possible, as soon as the time comes, I will be very grateful to answer any questions or any comments that may be addressed. Thank you so much once more for having this opportunity to present this project.
Thanks to you, Dr. Rodrigo Costa Felix, for your excellent presentation and being part of this annual conference on digital transformation in metrology. En este momento vamos a pasar a la última ponencia de este bloque y del día, denominada medición, procesamiento.
Now we're going to continue with the last block today, which is on measurement, processing, and artificial intelligence with partial discharges for the identification of faults in electrical insulation systems, which will be chaired by Carlos Boya. Carlos Boya has a master's degree and a PhD in electrical engineering, electronic and automatic engineering from the University in Madrid. He has been a scientific researcher and a professor in artificial intelligence, the processing of signals and electronic technology from the Inter-American University of Panama, as well as a leader in the electrical high-tension testing laboratories. He is the author and reviewer of scientific articles for international reviews with over 12 years of experience in applied data or science applied to electrical markets, high tension, biomedical and acoustics. He has participated in research in Panama in the National Research System for 10 years with field experience in distribution networks and as a designer, supervisor and inspector and project manager. Thank you for your participation and welcome to this conference. The floor is yours. Thank you. I'm going to share my screen. Let me know if you can see it. Yes, we can, Dr. Boya. I'm going to speak about a topic that we've been developing in Panama in the high tension testing laboratories. But first of all, I'd like to look at artificial intelligence in this field. The electricity systems are very important for the quality of life and are very related to high costs if they're not supervised. So it's important to understand the status of the whole system. One of the most important parts in the electrical systems are these electrical isolation. This could be mechanical, thermal, electrical. So over time, it's very important to monitor these constantly. And if this isn't done, degradation can lead to significant faults in the machinery, as we can see here. In these electrical cables, we can see the faults in these photographs here. These are generators that weren't serviced in time, and here because of contamination. All of this insulation is very short lasting, and it's I do apologize, but his sound is very unclear for interpretation. It's important to monitor this activity of the charges, because over time, if these problems aren't addressed, they can result in faults. So this is why a lot of different methods have been created to diagnose this damage. So this is just a scheme, somewhat simplified, just so that you can see how this is done. And looking at digital processing specifically. So machine learning is an important part of artificial intelligence. And we're going to explain in a very basic way the different forms: extraction, the detection, measurement, extraction, and the selection of the different characteristics and then the algorithms that allow us to automate the process of identification and classification. There are several standards here, and we have the physical and chemical effects we can observe here, a lot of different aspects. In our laboratory, we specialize on charge displacement.
And we work with other standards regarding magnetics, and there are other types of measurements as well. This is the typical measurement scheme for we normally use high tension sources, which are controlled to try to establish the tension. And there is a coupler, which is a type of sensor. The discharges are occur here, such as an electric discharge, and they generate other types of physical effects. So what we measure here is the electric discharges, and we use high frequency sensors, and we also use other types of sensors as well. So using these types of standards, we create different types of patterns, PRPD patterns, which allow us to identify the type of discharge which is being detected by the device. And with this, we can determine whether the device what type of damage is affecting the device, and we can also establish how the device is evolving and how soon it might be damaged. So here we are using this for other types of discharges and for collecting data. This is another one. This is the acoustic method, and this is used for gases. So there are different ways to analyze partial discharges, which provides us with information. And so this is the typical process for classifying machine learning. And now this is for collecting data, different types of anomalies, and these can be simulated anomalies. And we convert them with various types of extractors, and we select characteristics. We create a database for training and testing. And well, we train, we test, and we classify. And it's extremely complex because the electric teams depend on many variables. So we're still facing many challenges with in terms of machine learning. However, we are working as best as we can. So here we can see different types of characteristic extractors for partial discharges. So this is just a short list because there are many other techniques. However, we have the main ones here. I've worked in this field quite a lot. And here, in terms of machine learning, we have supervised and non-supervised machine learning methods. And you have the algorithms we use for classifying regression for the multiple tasks you might need to carry out. It's important to clarify that there's not one single method. It's not that we have to focus on one sole method. There are many studies, and it depends on what you want to diagnose and how you want to work. And sometimes you might have to apply several methods until you find the best one. So here you have an image or photograph of a laboratory. That's a high tension electric testing laboratory. We also have others for machine learning, for working with online data. We also have some with very good capacities, and it's also part of what we do here in Panama. So here you have some of the things we've been doing over the past few years. which shows the anomalies we might find, for example, in transformers, distribution lines. So what we do is we try to simulate these situations, and with the different types of measurements, we collect this data and try to automate these processes. So we have different types here. And one of the main problems we see in the field, because there are various types, is that we sometimes don't see just one type of anomaly. There are various types of anomalies in one device. So it's important to be able to work on new models and new forms of implementation that will help us differentiate. And that's because with this, we can diagnose the level of damage and how this evolves, and create an algorithm that will be able to help us collect data and generate data. So the thing is, this is something that is almost impossible. So this is something that will help us find the various different characteristics. So here you have different types of discharges, and sometimes it's difficult to differentiate. So now by implementing algorithms, we can label them and differentiate them, and help people work in the field. So this is something we are doing at in our laboratory. And there's something else we're doing as well, is analyzing the effect of environmental contamination in the isolators. So obviously we need other types of calibration systems in terms of measurements, and we need to consider various hypotheses to show that the algorithms can operate under different conditions. So what we're simulating here is isolators close to the coast, because that's what most seriously affects the equipment isolators. Here you have an image of an isolator which has been affected by salt. And this is a demonstration of the tests we carry out. So at the moment, we are testing, I'm not going to show you the whole instrument, but this is a simulation that's some of the tests we carry out. So that's the isolator. And we carry out measurements, and with those measurements we try to automate with an algorithm. We try to obtain information on when various events are going to occur, and this is related to diagnosis and preventing. So here you have a chart, and we use the sensors, which are similar to antennas, and we've made quite a lot of progress with this, and we're probably going to patent this. And these are discharges related to environmental contamination, and these are indexes we are developing, and these are going to create references in order to show us that the device might become damaged within a certain period of time. So that's something we are working on, and the purpose here is to develop a set of equipment and a solution for electric distribution companies. So this is a simple scheme we're going to be working on, or basically the scheme we're going to be working on: the discharge, the IoT with a signal and specific characteristics, and we already have several of these. We store them, and we obtain data to get the information and implement everything in an adequate manner. And alarms, for example, it's likely that the isolator will become damaged within a month's time. And this is valuable information, because I've worked with the distribution companies for many years, and it would be extremely valuable to have this information. So I think that this research and this work in the laboratory we're in is carried out with national and international support. We're working with the Inter-American University of Panama, with the Science and Technology Secretariat and the National Research System, and we're working with the Federico Santa Maria Technical University, and we're also working with the Technological University, with the Carlos III University of Madrid, and with the Soluciones Eléctricas de Chiriquí company. So I hope I didn't move forward too quickly, but this is what we're doing in terms of technical solutions. Thank you very much, Dr. Carlos Boya, for having shared this information with us and for participating in this annual conference on digital transformation in metrology.
As I mentioned at the beginning, for this blog, we will support by Dr. James Fitchak, whom I welcome once again, and I yield the floor to him. Go ahead, Dr. Fitchak.
Thank you, Jermaine, for the. Thank you also for the kind words you said in my biography description at the beginning. And I'd like to thank our speakers, Dr. Gilad Kusni, Rodrigo Felix, and Carlos Boya for their excellent presentations and participation in this conference organized by the SIM-MWG Working Group 14 for the transformation of digital metrology. So this is a really fun for me to listen to, because I am not an expert on AI or machine learning, and so it was an opportunity for me to learn a little bit more about this subject, which is going to be an important part of the digital transformation of metrology. And so I have a few of my own questions, and there's at least one question I see in the chat, which I think was answered, but I will repeat because not everyone has access to the chat, I think. But first, I have a question for Dr. Acosta from NIST. So in your presentation, you showed you're fitting these functional forms, and my question is are the functional forms ever what determines the forms of the function? Do you ever use physics to determine the forms of the functions? Do you restrict them by the physics, or is it not restricted by the physics in most cases? Gilad, are you on? Can somebody tell me if they can hear me?
This is the interpreter, and I can hear you perfectly well.
Okay, good. I just wanted to make sure. Okay.
Yeah.
Because okay. Did the speaker answer the question? Am I not hearing the speaker?
He did not answer. This is the interpreter again, but he hasn't answered.
Okay, let's go on to the next question then. So I will go ahead and read the question and the answer. So the question for Gilad Kusne was, did you consider any contribution of uncertainty from machine learning algorithms in your uncertainty budget? And also, which libraries are you using for your project? And the answer was, we use probabilistic methods that combine uncertainty from data and model. For Gaussian process methods, we use GPFlow and GPPyTorch. That's the easiest to use library called by GPy. So I believe that this is Python. For designing your own algorithms, we use Pyro, and he says he hopes it helps. So then I have a question for Rodrigo. So if this question makes sense, what would you consider the accuracy of the ARDS presently before this project started? How accurate is it at predicting this disease?
Okay, thank you so much for the question. I don't know, James, who asked that, but anyway, the fact is that we have no idea, have no clue about that, because as I mentioned, there are what profession from the health care part called scores. And scores, there's no metrology on that. They just say that if you have this image, there's some score. If you have that image, you have other score. But what separate and what are the uncertainty on the conformity evaluation is not clear at all. I don't know if you are aware about this kind of diagnostics on the healthcare area. People just use these figures or images and then say it's let's say let's use a more common example. When we have an ultrasonography of a baby, a prenatal baby, when the specialist, the doctor says it's a baby, it's because he's saying, because I cannot see a baby in any aspect, but it's true. It's because they are expert on that aspect in the evaluation of that image. But it's let's say subjective evaluation. What we are trying to do with this project is to make closer the evaluation of an image and what it actually represents. And so the question is, how is the accuracy now? I answer, I don't know. I know that there are some very well professionals that can do that, but there's no much metrology on that so far.
Good. There's a good project then. Thank you. That question was from me. There's a question for Carlos Boya from Susana Sanz Garcia. And it says, what technique did you use to classify the models or signals? How feasible would it be to install the insulator contamination monitoring scheme in electric power transmission or distribution lines?
Yes. Currently, use PCA and wireless transform with clustering techniques such as DB-scan, Camins, Gaussian mixture models, also neural network and deep learning algorithms about installing this distribution system and online measurements. Yes, yeah, they are currently carried out in electric machine such as generator, motors, and cabling, power cable, but is challenging. Okay, due to stochastic, natural stochastic of the partial reserve. Thank you.
James, your micro is off.
Thank you. Always a problem. Yeah, thank you, Carlos. And I have a follow-up question of my own, and that is something you may have mentioned in your presentation, but maybe you can remind us what kind of detectors are you using to detect the discharges?
Can you repeat for me?
Yeah.
you repeat?
Oh, I ask, could you tell us what, how you detect the discharges? What type of detector?
Electric conventional methods with ACE frequency current, high frequency current transformer, and galvanic measurements with a capacitor. Other sensor if with antennas. Sorry, my English nowhere. Okay.
That's okay. It's much better than my Spanish. Let's see. Are there any other questions? I do not see any more in the chat.
Others.
Well, if there are no, let me check one more time. If there are no further questions, then I would like to thank the attendees very much, and for the questions, and also to our three presenters, Dr. Gile Kusne, Rodrigo Felix, and Colas Boya, for being part of this third annual conference and answering the questions of the attendees. And for my part, it will be another opportunity. I give the floor to Jermaine, and thank you. And go ahead, Jermaine.
Thanks, thanks, Doctor.
Muchas gracias, Doctor Feldchak. Muchas gracias a los expertos por compartir y muchas gracias a usted por ayudarnos con el bloque de preguntas y respuestas. Thank you, Dr. German, and thank you to you for having helped us with the Q&A. Now, to finalize, I would like to introduce Fernando Kornblit to give us a few closing words. Go ahead, Fernando. Thank you, Germán. I would like to thank all of our speakers, all of our presenters today. I think you have given extremely interesting presentations, and this encourages us to continue working on this challenge that is digital transformation in metrology. So before we finalize, I would like to recommend that you visit the SIM page, and that you also visit the webpage of Group 14 on digital transformation by SIM, because they generally upload different types of information. And I would like to remind you that the Group 14 on digital transformation has the M4DT days. That's digital transformation days, where there are discussions, conferences, or presentations, which are all extremely interesting. The next M4DT day is on the 22nd of this month. So I recommend that you join the meeting on that day. So that's all I wanted to say, and we'll see you next year. So, well, see you then, or see you next time. Thank you.
Bueno, y agradecemos a todos los presentes en esta
We'd
conferencia.
also like to thank everybody who attended this third conference for your time, for your availability, for your questions. We'd like to thank our moderators and panelists. And as Fernando was saying, we will see you next time. Have a great day.